So this is Bluetooth packet sniffing using Project Ubertooth. My name is Dominic Spill. It wasn't until I saw everyone else's talks that I realized it's kind of stupid having a picture of myself on my slides because I'm stood in front of you, but in case anyone wonders, that's what I look like. I published a paper called Blue Sniff using software-defined radios to sniff Bluetooth packets back in 2007. Mike Osman, who was mentioned in the previous talk by Travis, he and I got working on the same stuff when he was working for the US government, and we used even more expensive software-defined radios and hardware hacked them to try and make all-channel Bluetooth sniffers. And what people used to do is come up to us after the talk. Is this? Oh, sorry. People used to come up to us after the talk and say, you know, I'd love to get involved in the project, but I don't want to buy a $2,000 radio and then take a soldering iron to it. I'd like something I can actually use. And as of a couple of months ago, I'm now the lead on Project Ubertooth because Mike has moved on to do other things. So can I just have a quick show of hands? Does anyone know what Project Ubertooth is? Know what the Ubertooth device is? Does anyone own one? Excellent. Is anyone actually able to use theirs? Oh, excellent, one. That's about the ratio we expect. I am not an employee of Great Scott Gadgets, but I do receive some funding from them, so they keep the lights on. I say they, it's Mike, it's just one person. And I'm not planning to sell Ubertooth here, Uberteeth, whatever the plural is, but they are currently, as far as I know, the only open source and cost-effective way to sniff Bluetooth-ish. You're going to be really disappointed if you expect me to sniff a phone call at the end of this talk, just to limit some expectations, especially with the demos having gone how they have this weekend. And a quick warning, I'm going to be running some Bluetooth scans in the next couple of minutes, and I'm not going to own anyone's phone or anything like that, don't worry, but a lot of devices, particularly MacBook Pros, tend to like to have the Bluetooth device name of Dave Smith's MacBook Pro. And so I know what all my neighbors have, and I know which ones have MacBook Pros and which ones only have iMacs, so I know which one I want to break into, and so on and so forth. So if you do want to turn off Bluetooth now, feel free to set it into non-discoverable mode if you think that'll help. And I think everyone's seen a few demos work this weekend and a few not work. I should also point out everything I'm doing is in 2.4 gigahertz range, and it's noisy, and we largely require reasonable data and low-level noise. So there's every chance that my demos won't work, but I have tried most of them out this morning and captured the output from them, so I'll at least be able to show you what they should do if they don't really work. So. Ubertooth looks like this. What you can see there is the chip at 45 degrees is an ARM processor. It's an LPC 1756 if you're interested in that sort of thing. The smaller processor just a bit further up. Where's my mouse? So this is the ARM here, and this one up here is the CC2400 chip from TI. It's a 2.4 gigahertz radio chip. It does the demodulation for us, and then we just stream back serial data. So this is a board that Mike Osman designed because everyone kept complaining that we were using these expensive radios. In fact, these expensive radios, and some people are a bit wary of spending $1,000, $2,000 on them and losing the lid and carrying them around like this and largely breaking them, but it's much easier when you didn't pay for it yourself. So we started talking about Ubertooth back in 2009 and saying to people, well, we'll try and build a platform. We'll try and build something that can do this. And this is what we came up with. It went through a couple of hardware revisions. This is the Ubertooth 1, which is what, if anyone's bought one, this is what you'll have. The Ubertooth 0, I think there were 10 of them, 4 of which worked. And I think most of them are in a drawer in my apartment. So it's entirely limited to the 2.4 gigahertz spectrum. It's basically limited to any radio system that is frequency shift keying modulated or something related to that. So Bluetooth 1, Bluetooth low energy, some Bluetooth 2 data. The difference between Bluetooth variants. There are now 4. They tend to suggest that the difference is to do with speed of data, and it's not. It's very subtly different to that. I'll come back to that in a minute. But the assumption, the marketing people would have you assume that a Bluetooth 2 device runs at 3 megabits and a Bluetooth 1 device runs at 1 megabit, and that's not actually the case. It's entirely to do with compliance to other technical standards and some strange little features that really get in our way. So it's all open source software and hardware. You don't have to buy one. I think they're $120 now. I haven't obviously bought one in a while. But I did buy mine. I actually thought it was such a good idea. I spent the money on them, so I didn't get them for free. But they're open source hardware and software, so you can go and pick up the designs, the plans. You can go and make one yourself. We know of 2 people who've bothered to do that. One built an Ubertooth 0 just as we brought out the Ubertooth 1, so naturally he wasn't too happy. And the only other time we've seen a home-built one was on eBay. So eBay in China, we saw a board that didn't look quite like ours and didn't come from one of our manufacturing runs. So, but we really do like it. So if anyone were to do it, I'm not fussed about making money from this thing. I'd love to hear if someone pop onto the main list and say, yeah, I built my own. So, so the first little application we run when we get the Ubertooth up and running is the spectrum analyzer, and it's just a standard 2.4 gigahertz spectrum analyzer, but it's just a nice little thing, and this just highlights my point of how much noise affects data that you can sniff. So these are 2 images captured from the spectrum analyzer within about a minute of each other in my apartment, and if you look at the top image, you can see, I can't find my mouse now, my Wi-Fi here on channel 3, I think. And my neighbour's Wi-Fi and things. And then this second one was after I switched on a very typical device. Has anyone got any ideas what it might be? Yeah, it's the microwave. So the microwave leaks an awful lot more energy than my Wi-Fi does. And that's probably because my microwave is old and the shielding's a bit knackered, but it's kind of a fun thing to look at to realise that, people say, oh, don't let your kids don't let your kids use Wi-Fi, but let them stare into the microwave as popcorn's cooking. So Bluetooth is the inspiration for all of this. I very recently added the line at the bottom of this slide which says it's a registered trademark of the Bluetooth Special Interest Group, just because I want to stay friendly with the Bluetooth Special Interest Group, and I don't want to upset them by misuse of their trademarks and so on and so forth. I think everyone knows by now it's 2.4 gigahertz. It plays with Wi-Fi and Zigbee's in the same band and all sorts of other technologies that you can grab. There are these 4 data rates, as I was mentioning earlier. There's basic rate, there's enhanced data rate, there's high-speed AMP, which is alternative MAC-PHY. What that does is it establishes a connection over Bluetooth and then switches to Wi-Fi, ad hoc Wi-Fi for the data transfer. It's actually a really nice solution to doing out-of-band key exchange. So it exchanges an encryption key, a random encryption key over Bluetooth, and then switches to Wi-Fi to transmit the data. For some reason, it only works at 24 megabits, but I believe there's a revision coming out that uses faster standards. And this works really well because almost every device you buy these days that has an integrated Bluetooth chip and Wi-Fi, it's all on one chip anyway. So there's no reason it can't work. And very recently, there's been the low-energy series of devices. The other thing you need to know about Bluetooth is that it frequency hops at 1600 hertz. So there are 1600 packets per second, all on different frequencies. There are 79 channels between 2.4 and 2.5 gigahertz. And it has a pseudo-random hopping sequence where it switches between these. And this is one of the things that has driven our desire to build custom hardware to sniff these things, because it's very difficult with commodity hardware. So, a little note about the Bluetooth Special Interest Group. It's a collaboration between many companies. It now has 17,000 members as of October 2nd this year, mostly because it's free to join. So that's a really great way to encourage membership. You don't really get anything for your free membership, although I'm planning to join as an organisation, we're planning to join in the next couple of months. They're actually really friendly. Their security team, the team who wrote some of the security for the for the spec approached us after a DEF CON talk in 2009 and gave us their email addresses and said, if you ever want to chat about security of Bluetooth, we're really interested. I believe the same people bought Ubertooth, so they're really interested and quite proactive in looking at security. Between the Bluetooth pin being cracked in Bluetooth 1 and coming out with Bluetooth 2 spec, they put a lot of effort into repairing the pairing mechanism. And while I like to spend my time trying to break Bluetooth, I do have to give them full credit for the fact that it's actually quite a difficult thing to break, and it's quite a robust standard, and it hasn't fallen in the same way as simply as early Wi-Fi encryption did. WEP and WPA went a little bit as well, and so on and so forth. So, but to encourage the reason for why we want to do this is the second half of this slide, which is there are lots of devices around, and they're growing at an amazing rate, especially with the incoming Bluetooth Low Energy. We're going to see low energy chips in almost anything in the next couple of years because it's so cheap and so low power to put in. You can run a Bluetooth Low Energy chip on a coin cell battery for over a year, so there's really no need to exclude it. And I'll just take a second to. It's on the wrong screen. I'm sorry about this. So every year, again, it's going to be every year the Bluetooth SIG run something called the Innovation World Cup, and they award funding to get their devices approved to people who want to invent a Bluetooth device and have some idea about how they're going to build new devices. And last year they were almost all Bluetooth Low Energy devices because that's what the marketing department wanted that year. And so we have things like a pair of headphones that also measures your heart rate through your ear, which seems kind of disgusting. But it's interesting that the other thing you'll note about all of these devices is that none of them have prototypes built. And part of the reason for that is if you look very carefully at the details, you're not quite sure how all of them will work. So this first one, for example, dual mode, it will work in low energy mode to sense your heartbeat and stream music to your headset at the same time. I have yet to see a Bluetooth chip that can work in both modes at the same time. In fact, I'm pretty certain that none of them can. And you can't, none of the heart rate measuring apps and so on and so forth for the iPhone yet will work with full speed Bluetooth. They'll only work with low energy. So you're kind of choosing while you're out there riding your bike on the open road like this guy is. You're choosing between listening to music or measuring your heart rate, which seems like you may as well just have two separate devices and run them separately. So I'm not sure the technical discussion has gone into these things yet. Someone's just drawn a picture and some weights. They seem pretty good. This one won and is also our favorite. It's going to use Bluetooth Low Energy to potentially control, where is it? Subcutaneously delivered drugs. The other nice thing about Bluetooth Low Energy so far, with the devices we've tested, is we've yet to find one that supports encryption. CapTrack. I mean, again, they're nice ideas, but I don't see any difference between having a Bluetooth Low Energy device on the top of a pill bottle that can tell you how many pills to take versus just writing it in marker pen, nice and big for someone to be able to read. I'm not sure what the advantage is here. And I'm a little concerned about the idea that my pill bottle might be reporting back to my doctor about whether or not I'm taking the medication and so on and so forth, and can you trick it and things like that. I'm not sure it's necessarily the great idea, but some of these are good. Some of them are not. I'm not entirely sure why you'd want an app to weigh your suitcase for you. So they've built a set of scales into the bottom of a suitcase, and as you pack it, it weighs itself. And this uses Bluetooth Low Energy to talk to your phone. It's an app, and I get that that's a great thing. It might be a really useful thing if you travel a lot, but why not put an LCD display on the suitcase and have done with it like that? Why do I need to have an iPhone and an app to weigh my luggage? And the airport are pretty good. The airlines are pretty good about weighing my luggage for me. Anyway, but my personal favorite is Forget Me Not, which is a locator device. So you put a little key ring on your keychain, and you lose your keys, and you open up this app, and it tells you whether your keys are in range. And this is like the Web 2.0, the app version of that little thing you could get in the 90s that you whistled and it beeped at you. But the big difference between that is high-pitched beeping is a very directional sound. You can hear it. Bluetooth Low Energy isn't. The antenna in an iPhone is non-directional. You can't use RSSI measurements to tell distance. All you can tell is that this device is somewhere within 10 meters or 20 meters of me, which is kind of what I know if I whistle at the thing. And if you, like me, you live in the middle of the city, if I stand in the middle of my apartment, I know my things that I've lost are within 10 meters of me because my apartment's only this sort of big. So I'm not entirely sure what the point of this thing is. It seems like it's another opportunity to sell something that everyone bought back in the day and decided they didn't want then. So, sorry, this is gonna, I don't know why OpenOffice does this to me. Okay, so I'll quickly run through some terminology. I think Travis covered some of this stuff in the last talk, and hopefully this won't take too long because I'd like to get into some demos pretty quickly. So Bluetooth devices have a MAC address like every Ethernet device or wireless device. You'll notice on an iPhone it happens to be like the same as your Wi-Fi MAC address +1. And in Bluetooth we split this into three parts. The NAP, which is the non-significant address part, the upper address part, and the lower address part. And you'll see in my diagram I've got an example. This example MAC address, so obviously MAC address is designed to be globally unique. The first half, the NAP and the UOP together give you the manufacturer, and then the manufacturer's role is to make sure that the lower half is completely unique within their device set. So this 001F81000830 is the only non-unique Bluetooth address I've found. And when I say non-unique, I've bought 4 Bluetooth dongles at different places at different times on different continents, and they've all come preloaded with the same address. Over here, if you buy a laser Bluetooth dongle, so you pick them up in like Big W, I think I grabbed mine, or maybe JB Hi-Fi, they claim to be a Cambridge Silicon radio chip, which was a device that everyone wanted a few years ago, and they're all the same, and that means they don't interoperate with each other. So be careful if you're picking up cheap Bluetooth dongles, because quite often they don't work as well as you'd think. So another facet of Bluetooth that we're going to need to know about in a minute is that there's an internal clock, which is 27 bits. It ticks 3,200 times a second. That's twice per frequency hop, and that's just because when we sniff for other devices, when we inquire for other devices, we do it at double the rate to make sure we hit all the different channels. So the packet is split up like many different radio technologies into, it has an access code at the beginning, which contains that sync that Travis was talking about in his previous talk, and it contains the LAP. So when you have Bluetooth devices, you have one master, and you can have up to 7 slave devices talking to them, and they talk in what they term a piconet. And the piconet is keyed on the lower address part of the master device. So that first section of the packet has that master device's lower address part, and so any other Bluetooth devices that pick up that packet know whether to bother decoding it or not, depending on whether it's their master device. When the slaves talk back to the master, they still use the same lower address part. All Bluetooth links are point-to-point. They're all master-to-slave connections. The slave devices, even though they're operating on the same piconet, they can't talk to each other. So you can't have your mouse talk to your keyboard. They have to go via the host system. And then we've got a header, and there's an error check on that, and then we've got a payload, and there may or may not be an error check on that. And that whole second part is whitened, which is much like the scrambling that you get on the 802.11b. And there's 64 possible combinations for Bluetooth for that, and we don't know what that is either. They're based on the internal clock value. And finally, there's non-discoverable mode. So that doesn't respond to me scanning for the device, but as I will show you very soon, many devices in that mode will still respond to information requests as long as you already know their address. And finding their address is very easy. And then there's the data whitening, which is just this XORing with the pseudorandom sequence, and it's a problem for us because we don't know it and we don't know the internal clock value. So we really need to get the MAC address of the device and the internal clock value to work out how to get this data out. So every talk we do, we put in a slide that says Bluetooth sniffing is hard. And we like to remind everyone of this because I get a lot of comments that say, Bluetooth sniffing, but we've been able to sniff Wi-Fi since 2001. And you could sniff Zigbee straight away. You just had to set the right bit on the chip. And Bluetooth is a very different protocol. And I think there's an awful lot of exploration of the Bluetooth attack surface that we can achieve once we've built a reasonable sniffer. And to exploit that, we need to build it, and it feels like we're way behind every other technology that has a packet sniffer because I can't just look at what's being sent over the air with my Bluetooth device. I can only look at what the host gives me. So I can't look for those corrupt packets, or I can't look for other people's packets or do anything like that. So I've got no idea whether my device is even using encryption. And believe me, it's probably not. So the things we really need, the frequency hopping, we need to know which channel to be on. They only last for 625 microseconds, so we kind of need to be on the right channel at the right time. That pattern's based on the part of the MAC address and the clock value. So to be able to get to the right packet at the right time, we need to know those values in advance. We also need to be able to undo that data whitening, for which we need the clock value. So the other thing, Bluetooth sniffing is apparently quite profitable if you can do it. There are 3 commercial, I'm not naming the names on the slide just because I'm certainly under NDA with one of them, and the others have never been particularly friendly. There's a device out there, in fact, if you buy the Texas Instruments low energy get starter kit, the dongle they give you will act as a Bluetooth low energy sniffer. But it will only act as Bluetooth low energy sniffer for a device which you tell it about. So you say, my device has this address. It connects to your device, syncs up its clock, and then just dumps all the packets. All it's doing is dumping the packets it can see because it's acting as a slave in that PicoNet and dumping everyone else's packets, which is a nice solution, but it's not something we can do with a commercially available $10 dongle. There's a very similar mechanism for Bluetooth basic rate. That's $10,000. And they never implemented a second generation enhanced data rate or any of the other versions with that. That is actually genuinely a standard dongle. This is why everyone wanted CSR dongles back a couple of years ago, because you could pull the firmware off that device or download it from a torrent or something like that, and which I don't recommend because it's apparently illegal. And then you could flash it to a CSR device and act as that sniffer. But even then, it still required you to tell it the address and allow you to connect to the device. And I've recently spoken to some people who still use these for work and for investigation. They say they just don't work with modern devices because these devices don't allow them to connect. So the iOS Bluetooth stack will just ignore that device. And then there's the 25 grand all-channel basic rate, enhanced data rate, low energy thing, and that's a pretty awesome piece of kit. It uses a super wideband radio to sniff all the channels and then channelize them internally and decodes them separately, and we believe may use, I don't know, but we believe it may use some of our code because we certainly spoke to them about it when they were first going into development. But if you're looking for something to commercially sniff Bluetooth and look at and examine the packets, that's the one to go for because it is very good. It's made by a company called Elysis, but it's also very expensive. And it's not really in the hands of a hacker anywhere, and it's like this big. So you go to a coffee shop and you pull it out and put it on the table and probably plug in your 3-phase power, and it's not gonna be very useful. So I'm gonna run through a couple of things we've done with the Ubertooth recently. Now we've been able to sniff the lower address part for a while, but we're very susceptible to errors. So there is a lot of noise out there that, as Travis was saying, gets in our way. We've been able to recover the UAP from the packets, so I'm not going to go through that, although I'll briefly touch on it just to make it known. And then I'll look at pairing the Ubertooth with other devices and trying to follow along with that hopping pattern as well. So the old method of finding packets, we used to take the incoming radio data. We used to move our way through it. We'd identify where in the packet we expected the lower address part to be. We'd pull it out, we'd try and create the packet around that, and then see if it matched what we received. We were incredibly susceptible to noise. If there was even a single bit error in the lower address part in the transmitted data, we would create a forward error correction that, because it's basically a checksum, would be very far away from the data that was being transmitted, and we'd get completely the wrong data. So this is what a packet looks like. Can everyone see the colors on that all right on the projector? The black section at the start is just background noise. The two red sections are a preamble and a trailer on the packet header. And the green section is our lower address part. So we take our lower address part, and we take this lower address part, and we create this section from it, which is forward error correction. It's just a, well, I'll tell you exactly what it is in a minute, but it's basically just a checksum. And we create that and try and see if it matches. But this was horrendously slow. It used to lock up my desktop PC. We used to get overruns from our hardware devices where they were trying to send us way more data than we could process. It was never going to work on an embedded device, and as I said before, a single bit error in the lower address part meant we generated entirely the wrong error correction, and we ended up with the wrong data. So, and there was no error correction. So I hit my head against a wall for about a month and implemented error correction. So has anyone ever played around with error correcting codes, specifically BCH codes? Reed Solomon? No one? Excellent. Consider yourself lucky. The BCH 6330 code is a forward error correction. So we generate a checksum and transmit it along with the data so that the errors can be corrected on the far end. This is used all over the place. It's used on every communications technology. It's used on CDs, DVDs use this, a very similar one to this. Reed Solomon encoding is the one used on CDs, which is just a special case of BCH code. The way BCH codes work is they generate this checksum, and then you should be able to take the data and calculate what's known as a syndrome, and the syndrome maps to an error vector, and then you get a set list of your error bits, and you can then XOR them with your data, and you corrected your data. And it's supposed to correct up to 6-bit errors. We see too many false positives at 4-bit errors to be even worthwhile using at that stage. So we only correct 1 or 2-bit errors. But the real kicker about this, we searched for implementations, and we asked around, and we said, it's amazing that they describe how to create that forward error correction, which we've been doing for a while, in the Bluetooth spec. But all the data about how we then take the received code and look for packets, there's no explanation of that. And why is it not in the spec? And the main reason is the manufacturers don't implement it. What the manufacturers do, because they always know the device they're expecting to see, they generate the forward error correction code that they expect to see. They load it into a register, and then as the incoming data comes in, they check against the register. So they never need to correct data because they're always looking for a specific set of data. So it's very easy for them to do this very quickly on very low-powered devices because you know what you're looking for. But that's not the case with a promiscuous packet sniffer. Once we know the address we're looking for, this is exactly what we do because it's the obvious and smart thing to do. But we had a very informal chat with a couple of device manufacturers and or chip manufacturers, and they said they haven't bothered to implement this in some of their chips because it's just not required. So the new method is we create an access code. We then say we're going to correct up to 2-bit errors. We create all the 2-bit possible error vectors, possible error access codes. We generate the syndromes from them, and we throw them into a hash table. And then when we receive data, we can look up those syndromes. Taking the error data, the received data, and generating a syndrome took me about 2 months to work out how to do the maths and write the code, and there was a lot of help from Mike Osman and various other people. Taking the syndrome and calculating the error vector from it, we have yet to work out how to do. And I mean, I spent a good month reading kind of lecture notes online from universities and various things. So if anyone has got any experience with forward error correction and these things, I'd love to hear how you calculate an error, the error vector from the syndrome. But realistically, again, you have to pre-calculate them all, which means we have to store a whole chunk of stuff in memory, which starts to rule out low memory platforms. But that's better than ruling out the low-powered platforms because memory's cheap. So I'm going to attempt to demonstrate this. So you'll see here that I am pinging from my laptop to this device here. This device is called a Kismet. Has anyone heard of the Kismet? It's made by the same guy who writes Kismet, and he decided that he needed something to be able to sniff Zigbee. So he built this device. It uses Bluetooth to communicate with an Android phone and dump all the Zigbee packets back to the Android phone. It's well worth looking into. Again, it's open source hardware. You can go build one yourself. So let me try and. Okay. Excellent. So there are people in the room scanning for other Bluetooth devices. You can tell because there's a specific lower address part that you're seeing quite a lot of there. Seeing a lot of other people's devices, but yeah, it's gone off screen now. There's it's 98B something 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 is the specific reserved lower address part that no one's allowed to use for scanning for other devices. So what you'll notice is we're seeing a lot of it's very difficult output to read. I'm just going to see this column here is our error. This is the lower address part. I really could have made the output to this much more pretty before trying to demo it to people. I'm sorry. You're not going to be any more pleased with the rest of the output because it's all text on a console. So we're able now to sniff packets at an incredibly accurate rate. We're able to correct errors in them, and we're now able to promiscuously sniff and identify devices, which is very useful when we want to do OpenOffice. Does anyone know how to get OpenOffice to remember which slide you're at? There we go. So this allowed me to, this week, write Ubertooth scan. Now, we've been banging on for years, and I think most people within the security industry who take an interest in Bluetooth know that non-discoverable devices are actually discoverable. All wireless communication is a broadcast medium. You're broadcasting packets containing your data out into the world, and anyone nearby can pick them up. It's not like Ethernet. You don't have a cable. They don't have to have the other end of the cable. They can just be nearby. So as long as you're transmitting, and your devices, if they're switched on and paired, are probably transmitting, then we can discover information about this. And you can see we can pull out the lower address part by looking at observing multiple packets and looking at the time gaps between them. We can calculate that whitening value and run the header error checksum in reverse and get the UAP. If you're interested in that, there's the 2007 paper, or there's the DEF CON talk from 2009 that's on YouTube and is worth looking at. But I'm just going to skip over and let's assume we can get the next byte of the MAC address for now. And very recently, Josh Wright coined a phrase called Wright's Law, where he said, security will not get better until tools for practical exploration of the attack surface are made available. And so on Thursday night this week, I hacked together a tool that takes the Ubertooth and pairs it up with and uses it with, I shouldn't say pairs when I'm talking about Bluetooth, uses it with a CSR dongle. It doesn't matter, any kind of Bluetooth dongle, and implements something I've called Ubertooth scan. And it's going to ask me for my password. So what this is currently doing is, first of all, it's going to run just a standard scan, as if you pulled out your phone and scanned for devices. And hopefully it should find my devices, which are all kind of hanging out here, or at least some of them. Excellent. I should have thought about this. So is that someone's iMac's come up there? Excellent. So what that's done, that's a standard scan. That's what you'll find if you scan for devices right now, or hopefully you'll find a similar thing. What we're doing now is the Ubertooth is doing that packet sniffing that it was doing before, just pulling out the lower address parts, and it's building up a hash of those lower address parts that it finds. As it goes through and receives more packets, it's going to try and sniff sniff that upper address part and calculate that from multiple packets and using the timing gaps between them. And then we've got the lower 4 bytes in the MAC address. Now, the upper byte is called the non-significant address part, and there's a reason for that, and that's because it's non-significant. And it's entirely, sorry, the upper 2 bytes, it's entirely useless. Okay, so it's not used at all. You can, using standard command line tools, you can ping and interact with the device, and you just set those top 2 bytes to 0, and it doesn't matter. It will never use them. They barely ever get featured. So no one, apart from myself, obviously, was stupid enough to leave a non-discoverable device hanging around. So also this is because I was able to pick up my data because, I'm transmitting from here to here and my sensor's here. I did turn the gain down a little bit just in case. But you'll notice that my non-discoverable device, that Ubuntu 0, didn't come up in the top in the top section. Its top 2 bytes here are 0, 0, which I can assure you they aren't on the real device. And then using a Bluetooth dongle, I used the BlueZ libraries, the libbluetooth libraries, and I connected to it, and it gave me all of its information. It gave me all the features it supports. It gave me the chip vendor. It gave me its internal clock value. And so this allows me to now know everything about this device, even though it's non-discoverable. So non-discover mode doesn't do anything. It still gives me all this advice. The only manufacturer that I know of that does anything useful with non-discoverable mode is Apple. And Apple devices will not respond to this kind of inquiry for a device that they've never seen before. So unless you've put your iPad into discoverable mode, paired it up with a device, and then disconnected them and turned the discoverable mode off, it won't ever give this information out.
Or you spoof something it has talked to.
Right, so this is the other thing. I now know this PicoNets. So the other thing this will only ever give me is master devices, because that's the only one that we're using. But as the gentleman in the front said, if you spoof something that it knows about, and it's very easy to spoof. In fact, if I do HI tool dev, you'll see I have 2 Bluetooth devices on my machine. You'll see the address on the second one is 123.456. It didn't come like that. You can set it to whatever you want. I've actually forgotten what it originally was because I originally intended to only set the address in non-persistent mode, and somehow I managed to write it to the flash. So now I'm stuck with it being 123.456, but it doesn't really make any difference to me. But you can. I've got a tool that I can just reset that address as I want. And my next piece of work that I plan to do over the coming weeks is to use that device to go out and inquire and try and talk to devices that might be slave devices. So I've got a mouse here that's connected to my machine. I've got the Kismet, and they don't come up in either of the scans because they're both. Oh, the mouse doesn't because it's non-discoverable. But I should be able to find it by spoofing this device, spoofing my main device. So that's my next angle of attack. Unfortunately, it was a bit late on Friday when I suddenly thought to do that, and there were a few too many beers had for me to have got any useful hacking done this weekend. So that hasn't happened. Quickly flick back to my slides. Stupid thing. So the thing that this talk was meant to be about originally was frequency hopping, and what we want to do is we want to be able to hop along and sniff the data coming out of this device. I mean, these devices are communicating. I've found them, but what are they saying? How can I sniff that data? So I wrote a tool called Ubertooth Follow, and this will, using the Bluetooth dongle in my laptop, connect to a device, grab its clock value, using its clock value as an offset from its own value, try and upload that to the Ubertooth. We know the MAC address and we know the the clock value, and we should be able to hop along and just dump that data. Before I do this, this works not particularly well in my apartment when there's not a lot of 2.4 gigahertz RF going on in the background. So I will say that I'm not entirely expecting it to work. Oh, need to unplug the Ubertooth and plug it back in. I broke the reset command. So there are two variants of this. One I've called follow local and one I've called follow remote. Follow local is the one I'll try and run now and we'll see what happens. Oh, there you go. So I'm receiving packet data. Now you'll notice a couple of things. One is a lot of this data is 0. That's because we're using enhanced data rate that uses completely different modulation. If I change my laptop to use low rate, or if I was using, for example, a headset or actually using the mouse, I wouldn't be seeing high rate data. The Ubertooth can't support high rate data. We haven't yet to find a chip manufacturer that builds anything that can support high rate data and just stream it out to us. So there may or may not be an Ubertooth 2 at some point that supports high rate, but I doubt it because Mike has recently launched a software-defined radio project that would probably collide with it in terms of price range, so it's not really worthwhile for us doing it. We may as well use a software-defined radio that's got more capabilities. You'll also see a lot of packet data here has type poll and type null because I'm just pinging backwards and forwards, and it's very easy to just use poll and null packets to do that. So I'm able to dump the data out from these devices. And what I used there was the local variant of follow. So what that did is the software looked at the chip in my PC that's actually doing the communication and just asked it for its details. And so just give me your clock value, and then it uploaded to the Ubertooth. I didn't have to make a Bluetooth connection to it because it's a local device. But that seems like a bit of a cop-out because who needs to sniff something that is attached to their computer? So I created follow remote. Again, I need to reset the Ubertooth. There we go. And what this is doing is it's creating a connection from one device to the other. Brilliant. That's completely not what I wanted to happen. It's trying to connect from one device to the other, pull in the clock signal, and upload it to my machine, to my Ubertooth, and have it sniff the data. Come on. There we go. So I've attacked a remote Bluetooth device. And if I wiggle my mouse a bit, hopefully what we'll see are these packets here, which are much shorter packets. They're going to the LT address, tells me which of my slave devices I'm talking to. And these are the positional information of my mouse. And as expected from a $25 JB Hi-Fi mouse, it doesn't support encryption. So I know the position on my mouse. Interestingly, my keyboard forces encryption, but my mouse doesn't, even though they use very similar price, low cost. And this is because obviously keyboards are much more, I can turn it off, but it tries to use encryption by default. But keyboards are much more important in this sense. Except my bank in the UK thinks that because keyboards are such a likely target, they get me to type in my PIN using a keypad and a mouse. So if I know how the mouse is moving, I know what the PIN is, even if I can't read my username, which I type with the keyboard. So I don't see that that's any excuse not to implement encryption. It's not difficult to implement. Most of the chips support it. The chip in this supports encryption. They just haven't turned it on. So. Stupid thing. Oops. So the pros of that are that it's reliable-ish. There's a chance to sniff pairing. I can find out the details of the device, and if I sniff at the right time, I can grab that elusive pairing and try and crack the PIN between the devices, crack the crypto, something along those lines. But it's kind of bad in that I'm using another Bluetooth device to do it, and really we should be able to implement this. We should be able to work out what the clock is. AFH support it's not something I've particularly spoken about, but previously Travis mentioned that the Bluetooth and Wi-Fi don't coexist very well. They don't have any mechanism at the low layer to work out how to coexist. And so one way to manufacturers implement this is AFH. Now, AFH is actually one of the things that is required for Bluetooth 2. If a device says it supports Bluetooth 2, it supports adaptive frequency hopping. And what this means is it looks at my Wi-Fi chip, it says, what channel's Wi-Fi on? Okay, I'm not going to go there. And so it avoids my Wi-Fi chip. From a sniffing point of view, this is a pain in the arse. We can attempt to calculate the frequency hopping map. We can survey the channels and do that and try and find that. There's a key sign that you're using adaptive frequency hopping, which is you see back-to-back packets on the same channel because it hops half as often. But we don't fully support it because we made the assumption a lot of the time when we're writing this that it wasn't used in the wild, which it wasn't at the time. But now that absolutely everything is Bluetooth 2 or higher, including my mouse, which was dirt cheap, then I don't have much choice other than to support it. So I imagine, again, that's something I'm going to work on over the next couple of weeks, is just to make that work. But that's one of the things, again, which is killing the demonstrations here for me. The data rate of that data rate should have been much higher, but I'm missing half of the packets because it's doubling up on the packets, and sometimes I'm on the wrong channel. So apologies for that. Clock drift is actually not as much of a problem as it could be, but because we're not actually synchronized and we're not transmitting packets with the device, our two clocks skew over time. That's something I fixed very recently, so it's actually not as much of a problem as it used to be, and the more practice we have with this, the better that'll get. But what we really want to do is work out that clock rather than having to just ask for it, because the easiest thing to do there is just to not give it out. Apple don't give it out, so all the other manufacturers will change their stacks to no longer give out that data to unknown devices. So really we want to do it without having to connect to the device. And this is where Ubertooth hop comes in. Now, this is slightly complicated, but I'll try and very briefly, because I'm running out of time. The hopping pattern loops every 24 hours. It's pseudo-random, but once you've got the MAC address, you can calculate the entire hopping pattern. So we calculate the hopping pattern in memory. We look at where we've observed packets, which channels we've observed them on, and at what time. And then we take those packets, those positions, and we apply them to the hopping pattern, and we try and find where that uniquely fits in the hopping pattern over the course of 24 hours. And in theory, it takes 5 packets, and in practice, it doesn't. It takes a lot more. So this is hopefully going to work. Completely forgotten what I called the demo. Clock. So this runs a tool called Ubertooth Hop. I've just thrown together some shell scripts to make my life a bit easier, and then forgot their names to make it a bit harder. So what this does is it's looking for packets, specifically packets from my laptop. I gave it the details to just say, go for that Piconet, the details we pulled out before. And hopefully at some point it should stop and say, hey, I found the clock value. But largely it doesn't. That's the other way. If in doubt, pull the thing out, plug it in again, and start again. So it calculates the entire pattern, throws it into memory, and there we go. So using only observed packets, we've derived the internal clock value of a remote Bluetooth device. And we can then take that value, upload it to the Ubertooth, and start hopping along and sniffing the device. So it basically looks exactly the same as the previous demo I did. You can't tell the difference, so I'm not going to do it because I'm running on time. What was that to say? So Ubertooth hop is given a specific Piconet. It finds clock and hops along. There's a Kismet plugin. It's really not that interesting. I'm going to skip the demo, but it does dump data out in PCAP format. There's also a Wireshark plugin to decode this. So if you've captured data and you want to load that into Wireshark, you can, and it will decode the data for you. Let's see if I've got Wireshark. So I've got a couple of seconds to do this. So you can see that the Bluetooth data is dissected, and you can pull out the data from that. This is from a ping that I did earlier and captured with Wireshark. We've got some sample files of like mouse movement and things like that. You just pick it up using Kismet and dump it to file, and then you can read it and analyze it offline in Wireshark. One of the things you'll notice is the pole and null packets. Bluetooth devices like to do these a lot just to make sure they're still connected. If I haven't got any data, I'm still going to send packets back and forth. So even if you think your devices aren't communicating because you're not moving your mouse or you're like mine that turns itself off after a little while, it's still sending data back and forth, and I can still pick up that data and calculate the clock value from it. Anything else? Kismet Plugin, Wireshark. Bluetooth Low Energy, very quickly, because I haven't done much of the work on this yet. Bluetooth Low Energy, there was a test board produced by TI about 18 months ago, and once the board was produced, it took about a week before we could sniff packets. And then we largely left it alone until this August, and a guy called Mike Ryan came up to us and said, "What's left to do in Bluetooth?" And we said, "Everything, but if you want a project, how about low energy?" And so tomorrow morning he's speaking at TalkOn about how he's now able to sniff a pairing, capture Bluetooth low energy device data, and dump it back to the host. He does this specifically with a heart rate monitor. I couldn't get my hands on one before the event, so I wasn't able to try out the code and demo it for you. But if anyone has one of those Polar H7 heart rate monitor things, if you've got one, doesn't use encryption. You probably don't care because it's a sports device, it's not a medical device, but I'm almost guarantee that the medical devices that are coming in the next year will be based off the same chipset and the same sensor, and someone will probably have to give them a kicking before they implement encryption. So that's definitely coming soon. They implement AES encryption, which is much nicer than the custom algorithms used for Bluetooth, but they the key exchange is potentially flawed. So adaptive frequency hopping, encryption, sniffing a pairing, transmit, implementing a full low energy I've got food on the mind. Stack on an Ubertooth. We're hoping to maybe get like a Google Summer of Code student to do that, because we think it'd be kind of fun. Getting all that follow stuff into the Kismet plugin. I've got a device up here that you can see has an SD card on it, because the thing speaks SPI. So why don't we sniff and store the data and post-process it later? Just run an Ubertooth from a battery. And embedded platforms. We've already had some of the code work on Android. We've had some of someone's looking at OpenWRT support. I've got a Wi-Fi Pineapple that I'm supposed to get it running on at some point. So there's a huge amount of future work, if anyone's interested. Unfortunately, I'm not in a position to give out hardware, but I am more than happy to be as helpful as possible to anyone who's interested in playing around with this stuff. And just quickly, thanks to Mike Osman, who obviously created the device and I've worked with a lot, Jared Boone, who wrote a lot of the code, Mike Kershaw of Kismet fame for all his help, some guy called Will Code who just turned up on the mailing list one day and started submitting code. We have no idea what his real name is or where he's from, although we're narrowing it down by time zone. Mike Ryan, who's just appeared in August and suddenly took over low energy stuff, saving me a lot of work. And this guy called Zerocas, who's a Gentoo submitter. If you want to get the code working and you want to get up and running as quickly as possible, Gentoo is the distribution to use. The build instructions are about a page long for any other distribution, and for Gentoo it's one command. And that's largely thanks to the fact that the Gentoo guys are really helpful, and Debian are not. Oops. Sorry. And then the last slide just said questions, which I probably haven't got time for, but I will be outside if anyone wants to talk to me about it.
All right, well, let's thank Dominic. We have time for just probably about one or two questions.